So appreciate everyone coming in today and spending some time over this hour to talk about Mojave. Um, to set the stage very briefly, Mojave has a liquid desiccant-based DOAS product. So conceptually, this is an outdoor package-style rooftop product where we pair together liquid desiccant technology with DX technology to create this uh, DOAS product and dehumidification product that's about 50% more efficient than conventional DOAS products and has a much wider range of operation. It has the ability to deliver much lower dew points, if desired, than conventional DOAS products, down into the 40 degree dew point range. So agenda for today, we'll start off with a quick Desiccants 101. We'll cover Mojave's background as a company. We'll look at a new efficiency metric regarding dehumidification called ISMRE. We'll also do a product introduction. We'll look at operation and maintenance, and then we'll close things out with how to apply dew point depression for simpler and more high-performing buildings. Very briefly, my name is Kyle Troskot. I'm the Director of Rep Sales for Mojave Energy Systems. Was a sales engineer for quite a while prior to taking this role. I have been with Mojave for about a year. So to start with the Desiccants 101, let's define a desiccant. What is a desiccant? A desiccant is a solid or liquid material used to absorb or adsorb moisture from the surrounding environment. The most common solid desiccant that you've ever come in contact with is a silica gel packet, shown on the screen up here. Liquid desiccants, a good example of a liquid desiccant is the Dead Sea. That's a naturally occurring liquid desiccant. Basically, liquid desiccant is a high salinity brine solution. Now, liquid desiccants are industrial brines, so we're using lithium chloride as our desiccant agent. And lithium chloride is shelf stable, it's non-reactive, it's non-vaporizing as well. It has vapor pressure of 0.7 psi at 1445 degrees Fahrenheit. It is also a biocidal agent, meaning it is a natural air cleaner. It'll kill molds, bacterials, and microorganisms. Hence, the Dead Sea is an example of that. Liquid desiccant is also a antifreeze, natural antifreeze, and has a freezing point below minus 40 degrees Fahrenheit. So some basic terms and points about desiccants. The strong affinity for water molecules is the hygroscopic nature of solid and liquid desiccants, meaning it has a strong affinity for water. Liquid desiccants and solid desiccants as well, both are a function of vapor pressure. Desiccants exhibit a low vapor pressure to attract moisture from the surrounding environment. When the vapor pressure equalizes with the surrounding environment, the absorption or adsorption process ceases. So, technical term for removing moisture from desiccants is regeneration or reactivation. Those terms are used interchangeably in the market depending upon manufacturer. Many desiccants can be regenerated by removing the adsorbed or absorbed moisture, making them reusable. So for example, by heating or drying, some desiccants can release the trapped moisture and be used again. And then desiccants are not a new technology to the HVAC market. They've been employed both solid and liquid for 50, 60 years now. So desiccants, solid desiccants, liquid desiccants, not a new technology at all in the market. Additionally, desiccants are used in a wide array of applications, everything from those little silica gel packets I just showed you to drying process for industrial dehumidification. So used across a wide range of applications, as well as even refrigeration applications where you need dry and cold spaces. A little bit more on liquid desiccants. So to conceptualize a liquid desiccant for everyone, if I put a pile of liquid desiccant in front of you on the table or on the desk, wherever you're sitting or listening, liquid desiccant has a very low vapor pressure, as I said before. And what it is a concentration of salt or an amount of salt and amount of water mixed together as a solution. And what's happening is liquid desiccant has a very low vapor pressure. And when exposed to a higher vapor pressure air, or saying that differently, air with a higher moisture content and a higher vapor pressure, nature likes to be in equilibrium. And what happens in that process, there's a natural draw or a passive process where moisture is pulled out of the air into that desiccant puddle that you're looking at here. So what's happening, you pull moisture in a puddle, that puddle is going to start growing in size because it's an absorption process. So that salt content in that puddle stays the same. The water content in that puddle changes. You get a volume change. As a result of that, the puddle grows in size. Now, to get the moisture out of that puddle, as I said briefly before, you add heat to a desiccant and you evaporate. In liquid desiccant terms, you evaporate the moisture out of the desiccant, removing that moisture, which goes back into the ambient environment. Again, salt content does not change. Water content changes. The volume of the puddle shrinks. And as you take that heat away, the process repeats itself. You go back from this state to this state where you pull moisture back in to grow the size of the puddle, add heat to remove the moisture from the puddle, and that's what we're doing fundamentally with the system. So I've thrown around the words adsorption and absorption. Let's define those briefly. Adsorption is where particles stick to the surface of another phase. This is what solid desiccant wheels do. You have water molecules, they stick to the surface of a solid desiccant material. Liquid desiccants use an absorption process with a B, and that's where we have those water molecules coming into that desiccant puddle from my example on the last slide, growing that volume. And as they release that moisture, the volume shrinks. So liquid desiccants are using an absorption process with B. So from a dehumidification options, there's several different products and technologies out there that can be used to dehumidify. You have vapor compression, chilled water, liquid desiccants, and solid desiccants. Vapor compression products, from a dew point perspective, can achieve dew points I've seen anywhere between, at the extreme low end, 45 degrees dew point. Most manufacturers can achieve somewhere between 45 and 48 degrees dew point with their vapor compression style systems. And that's your traditional hot gas reheat DOAS style system, DX style system. Chilled water, similarly, if you have 42 degree chilled water, about maximum dew point capability is somewhere between 45 and 46 degrees dew point. Liquid desiccants, and specifically Mojave, can achieve dew points as low as 40 degrees, all the way up through that traditional range of 55 degree dew point for conventional projects or applications. And then solid desiccants as well can cover the entire range, but typically we don't see solid desiccants in the commercial market due to the price premium that they command. So switching gears, a quick background about Mojave. We have a pretty interesting background. We came out of a very famous R&D lab called PARC, or Palo Alto Research Center, which is a famous R&D lab subsidiary of Xerox. This R&D lab is responsible for a number of really interesting technologies or game-changing technologies in the commercial environment. Obviously, laser printing and Xerox. They're also famous for coming up with Ethernet, the modern personal computer. They have a claim to fame working with Apple on that. As well as the computer mouse. Now, under a clean tech initiative, they also were looking at how to impact the built environment, reduce energy spend, and landed on liquid desiccants as a way to reduce our energy spend in terms of dehumidification in the built environment. So during the process of 10 years and tens of millions of dollars in R&D money from NREL, Department of Energy, as well as PARC and Xerox. What is now Mojave has spent time working on how to leverage liquid desiccants' absorptive capabilities, as we just discussed, while overcoming their material handling challenges. I'll get into that a little bit later in the presentation. But in short, once we figured out the material handling challenges, the company was spun out. We are currently in manufacturing, and we're manufacturing in Anderson, South Carolina, with a lead time between 13 and 16 weeks. So talking about the built environment, things have changed a lot with buildings over the last 100 years. We've gotten, frankly, much better at building buildings. And this is really being driven by 90.1. We're using better insulation, low emissivity glass, cool lighting, and we've gotten much better at moving thermal energy around. So VRF systems, using efficient ventilate or using chilled beams, etc. We've gotten very good at efficiently moving BTUs around buildings. On the flip side, 62.1 is encouraging us to bring in more outside air for a healthier built environment. So for IAQ purposes. Additionally, ventilation rates are now being sized based off maximum occupancy. So while our buildings have become more efficient thermally, our latent loads in buildings are flat, if not have been increasing, meaning we're bringing in more humidity than we ever have, while our thermal loads or sensible loads in buildings have been dropping. And as a result of that, what's happening is our sensible heat ratio in buildings is dropping. So we have a lot more humidity to deal with, and that's really what we're trying to address with this liquid desiccant technology, is how to efficiently dehumidify in buildings. We haven't really seen a whole lot of innovation in that segment. For the last 50, 60 years, all we've been doing is condensing moisture on a coil. Surely there's a more efficient way to do that. We think liquid desiccants is the answer to that. So there's a new efficiency metric that was just released here in 2022 by the Department of Energy. This is called ISMRE, or Integrated Seasonal Moisture Removal Efficiency. Came into effect in 2022. Manufacturers starting May 1st of 2024 have to comply with this nationwide, and this is regardless of local and state codes. Basically what it states is you shall have, according to the table on the screen here, for air-cooled, air source heat pump, water-cooled, and water source heat pump systems handling dehumidification and ventilation, an ISMRE2 value above these stated minimums. And what it's looking at is how much moisture can you remove, or how much water can you remove from the air per kilowatt hour of input. So how much energy, or how much water can you remove from the air for each unit of energy input. Similarly, this is like IER for DOAS. It is a simple conceptual parallel. So IER is how many BTUs can you remove per kilowatt hour. ISMRE is how much water you can remove per kilowatt hour. And this is in ASHRAE 90.1 2019, as well as IECC 2021 and beyond. Regardless of local and state codes, though, at a federal level, if any DOAS manufacturer, dehumidification manufacturer wants to sell product in the United States, you have to comply with these federal minimums. What does this actually look like calculation-wise? It's a weighted metric, very similar to IER. So focused on higher latent points and how efficiently you're pulling moisture out at a defined set of points. And the intent here was really to provide the consulting community and owner community a apples to apples way of comparing one dehumidification product to the next, to the next, to the next. So a higher number equals a higher efficiency, just like IER. A 17 IER rooftop unit is more efficient than a 14 IER rooftop unit. Similarly, a 10 ISMRE2 is more efficient than a 6 ISMRE2 unit in terms of dehumidification. So in summary, I would suggest that when you're evaluating dehumidification and DOAS products, not to look only at EER and IER, but to look also at your moisture removal efficiency or integrated moisture removal efficiency when comparing products out there to determine the best product for your application. So, quick example from a design perspective. One thing I've seen a lot out there is a lot of engineers only look at a cooling design day or specify only a cooling design day for their DOAS and dehumidification applications. I would encourage design engineers to review not only your cooling design day, but your dehumidification design day as well. And the reason for that is typically the enthalpy on a dehumidification design day is actually higher than your enthalpy on a cooling design day. So even though it's not as hot, quote unquote, outside, there's a lot more moisture content in the air. And to pull that moisture out of the air, it takes a lot more energy and frankly capacity to do so. This is an example in Houston, where your cooling design day is 105 and 76.6. You have about 22 tons of cooling required to hit a 50-degree off coil. Now, under a dehumidification design day, only 82.9 outside, dry bulb, 79.4 wet bulb, you actually need 25.5 tons of capacity. So just to give you guys an idea of what kind of delta you're looking at if you're only sizing around your cooling design day. So under a dehumidification design day, if you only sized around cooling, you would actually be undersized and not be able to achieve the target condition. So best practice, I would suggest that you look not only at cooling design day, but also dehumidification design day, as that may drive your peak load condition. So switching gears a little bit, why do you care about all of this? Those federal minimums I showed you a couple slides ago are these green bars on the graph. So 4 pounds, or pardon me, 3.8 pounds per kilowatt hour of moisture removal efficiency without an ERV, 5 pounds with. Mojave Arc to Dry is pushing 8 pounds per kilowatt hour of moisture removal efficiency without an ERV, and 10 pounds plus with. Now, additionally, because we've paired together DX technology with liquid desiccant technology, we've effectively decoupled our dry bulb and dew point control. So Mojave Arc to Dry can take a dry bulb set point and a dew point set point and control each with our system. So much more precise level of control due to that decoupled approach in terms of hitting set points and meeting application demand. Additionally, with the pairing with liquid desiccant technology, we're able to deliver dew points that were originally only achievable with industrial level equipment. We could achieve dew points as low as 40 degrees, in some cases even lower, down into the 35 degree dew point range. Now, from an energy spend, liquid desiccants, as it's a passive dehumidification process, really there's conservation of energy happening as we dehumidify. And as a result of that, I'll discuss that more in detail in this presentation. But as a result of that, we're about 50% more efficient on average than a conventional vapor compression hot gas reheat style system. From a installation side of things and a simplicity side of things, conceptually, there's a lot going on with liquid desiccants. I'll show some screenshots of what's going on in our product. It's actually a very simple system. Additionally, no makeup water required with this style of product. It's purely an electric integration to get up and running. From a payback and ROI perspective, we're positioning this to be a small premium over hot gas reheat style products, but that ROI on first cost should fall well within that first, or that 1 to 3 year payback on ROI, depending on what location you are geographically. Additionally, this does fall into the decarbonization portfolio. We're offsetting about 33% of our refrigerant volume in our units with liquid desiccant. So only 67% of the refrigerant of a conventional hot gas reheat system in our product. Hardware-wise, we have 2 cabinets currently, a 1 to 3,000 CFM cabinet, as well as a 3,000 to 6,000 CFM cabinet. We are already using 454B refrigerant. That's that new A2L refrigerant. This is a variable speed driven system, so variable speed compressor. It is an inverter compressor, not a digital scroll product. We are using ECM supply fans capable of 3 inches external static, as well as regen fan and condenser fan are AC with VFD driven. Double wall construction, foam injected panels, R13 insulation. Controls wise, it is factory packaged controls and pre-programmed as well. That said, we could work on custom sequencing if required, but it is factory packaged controls at BACnet, MSTP, IP, Modbus is all standard. Additionally, we are providing a cell modem on every product, made available at no additional cost to the end user, capable of remote monitoring, diagnostics, and trending. Beyond that, we do offer a built-to-spec style a la carte menu of options, some of which are listed on the screen here. And we have a bunch of additional options not listed here, but a la carte, built-to-order style product. So what's in the box? Unlike traditional DOAS products, going back to my example of that puddle, when we pull moisture into desiccant, we have to get that moisture back out. So there takes two air paths to do that. You have a process air path or supply air path up here on the top, if you guys can follow my laser pointer. This unit can do everything from 100% outside air to mixed air to 100% recirculation air for straight dehumidification. And then you have a secondary air path. This is not connected to the building at all. You're taking outside air in, putting it through a heating coil, evaporating moisture from the desiccant, and then dumping it right back outside. So fundamentally an outside air tunnel, no connection to the building, no cross-contamination with airstreams either. So what's happening here is we're taking outside air in on our process side, passing it through a DX cooling coil. And what's happening is you're cooling and doing partial dehumidification with this cooling coil. Coming off this coil saturated, anywhere between 60 degrees and 75 degrees Fahrenheit dry bulb, 100% RH. And then you pass that cool, saturated air through our humidity absorber. I'll show what that looks like on the next screen here. And basically what's happening is as you pass through this humidity absorber, that high vapor pressure saturated air is interfacing with the low vapor pressure of our liquid desiccant, and that passive dehumidification process begins. And what's happening here is you're condensing moisture out of the air, going from a vapor state to a liquid state. It's a latent heat of condensation. So for saying that differently, for every iteration of dehumidification, you get equal parts of heat associated with that released back into the air. So there's a conservation of energy happening. You're converting latent energy to sensible energy. So you actually get passive reheat as a result of this dehumidification process. So going back to high school chemistry days, you call this an exothermic reaction. So to summarize, as we come out of this absorber, it's doing dehumidification and heating, providing neutral air to a space, and this air can be anywhere from 55 degrees dry bulb to 75 degrees dry bulb, and anywhere between 35 dew point and 55 dew point, and that's all actively controllable. Now, for control of the dew points, we're able to do active dew point reset. The way we achieve that is by regulating our hot gas via this modulating three-way EEV. For days where we need more dehumidification or peak dehumidification, we're going to be routing a majority of our hot gas off the compressor into this regeneration coil to drive more moisture out of our desiccant, to heighten the concentration and lower the vapor pressure further to pull more moisture out of the air in this humidity absorber. In days where we don't need as much dehumidification, so part load days, we may route a portion of hot gas to this coil, and a portion of hot gas will just dump to ambient via conventional or traditional condenser. So a couple other things here. Liquid desiccant, unlike solid desiccants, for anyone who is familiar with solid desiccants, will thermally cycle infinitely. The reason for that is just a crystalline salt structure. Again, it's a biocidal and natural antifreeze as well. From a maintenance perspective, liquid desiccant being a situation where it'll thermally cycle infinitely, never needs to be replaced. And through elegant engineering, which I'll talk about in a second here, it never needs to be topped off or what have you either. So how are we interfacing liquid desiccant with the airstream? And that's through this humidity absorber here. Looks somewhat like an evaporative cooler, is very much not. Frankly, it's doing the quite opposite, or the exact opposite of an evaporative cooler. What we're doing is an impregnation style falling film, and you basically have milliliters per minute flow rates of liquid desiccant running down these channels while the air passes through this media. Now, we've looked at face velocity, flow rate of air, flow rate of desiccant, surface tension, media, and geometry to all determine and test out to single-digit parts per billion with a B that we have basically created this closed loop system where desiccant is not being pulled out of this media into the airstream. We do have a white paper detailing that process, but it is effectively closed loop in the sense that nothing comes out of this media. Then to finalize that thought, we do have a 3x safety factor on face velocity as well with our system to ensure that we don't ever put ourselves and our equipment at risk of pulling desiccant out of this media into the airstream. So what does this hardware actually look like? Like I said, lots going on here. Conceptually, from a hardware standpoint, there's actually not a whole lot going on in the box. You have your outside air intake, and this could be a return air intake as well for recirc applications, a return air knockout if you're doing a mixed air application, or a bottom return 100% recirculation style application. You have a cooling coil, which you'll notice is not a particularly deep cooling coil because we're not doing all of our dehumidification with a DX system. So coming off that coil saturated, as I suggested before, and then we're passing our saturated air through our humidity absorber, which is a static media within the airstream, so no cross-contamination between the two airstreams, no carryover of heat between the two airstreams. And this media is being pumped, gravity-fed, impregnation-style falling film of concentrated desiccant, which runs down these channels, condensing moisture out of the air into the desiccant, trapping it. We have a pair of fractional horsepower pumps circulating desiccant through this media as well as to the other side of the unit to remove that moisture from the desiccant so the process can be repeated. Downstream of this, we have our winter heat option. So if you want to do gas heat, electric heat, hydronic heat, VRF air handling kit heat, we can accommodate all of those. No air source heat pump option yet. We're about 12 months away from releasing that product, but it is on the way. And then configurable down discharge, side discharge. Here's our ECM supply fan, again, capable of 3 inches external static, and then your compressor access down here. This is our A cabinet up to 3000 CFM and down to 1000 CFM. Now, a couple other things here. All of our panels are dual-sided panels and dual-sided hinges, meaning they could come off from a service perspective. So every one of these hinges can be opened and the whole panel can be removed for service. Additionally, protecting the desiccant system is a pair of T-strainers. As long as you have at least 3 fingers and a thumb in one hand, it's something that is unscrewable. You rinse it out, you put it back in. That is the only maintenance on the desiccant system itself. Outside of that, I'll talk about maintenance a little bit later in the presentation. We do have those pumps on independent breakers. So if the unit is not being maintained regularly, which we suggest quarterly, filter changes and inspection of those T-strainers. If that's not happening and those T-strainers back up, the pumps are on independent breakers and will trip on high draw, acting like a dirty filter switch would to alert the unit or alert the user that, hey, the product needs to be serviced. Now on the regeneration side, just to give a visual of that, quite literally an outside air tunnel, you pull air in, there's a coil behind here and a fan. You heat that air up, pass it through another media like the one I've shown, evaporate the moisture that you've collected in that desiccant out, and dumping that moisture back to the ambient environment. So going back to this slide for 1 second, very conceptually, we're moving thermal energy or BTUs from one stream to the other via refrigerant, and then we're moving moisture from one stream to the other with liquid desiccant being that medium. So visually here, I showed you the A cabinet up to 3000 CFM, a quick visual of our B cabinet up to 6000 CFM, just to conceptualize that. And then, just as a reference point, a little bit more granular detail on our refrigeration circuit on the left here and our desiccant circuit on the right here. So switching gears, for those on the line that are familiar with solid desiccants, a couple things to keep in mind when comparing a liquid desiccant versus a solid desiccant. From a moisture absorption capacity, solid desiccants are fixed due to the fact that it's a fixed media. With liquid desiccants, it's variable and it's based on the volume of desiccant within a system. With regards to lifetime, solid desiccants do degrade over time and have a degradation factor. Typically, it's anywhere between 5 and 10 years, depending on manufacturer of a solid desiccant wheel. With liquid desiccants, it's infinite. One of the key benefits of liquid desiccants over solid desiccants is the regeneration and temperature control. With solid desiccants being a fixed media, it is static. So regardless of whether it's a peak operation or a part load operation, that desiccant wheel is pretty much going to do the same thing every time. There's very little flexibility in how to manipulate its dehumidification capabilities. With a few asterisks on that, which I won't go into, but I'd say reach out to me after the fact and we could discuss if you'd like to. On the liquid desiccant side of things, as its concentration control and your vapor pressure of the liquid desiccant is a function of concentration, you do get a lot more flexibility from a manipulation standpoint. So on a peak day, you could drive up the concentration to dehumidify more. On a part load day, you could relax the concentration to dehumidify less. You're not consuming more energy than you would typically, or than you would want to with a liquid desiccant. Solid desiccants, you have a wheel that's rotating between airstreams, so you get parasitic heat crossover. Solid desiccants have to be regenerated up into the 200 to 300 degrees Fahrenheit range to get all the moisture they've trapped out, so the process can be repeated. There's a lot of parasitic heat crossover between airstreams as a result of that. With liquid desiccants, there's very low, and frankly, with our product, negligible crossover of heat between the airstreams because we're not really interfacing the airstreams. They're isolated. There's negligible amount of heat being brought over in our liquid desiccant as a medium. A couple other things. There's no benefits around IAQ with solid desiccants. With liquid desiccants, they are naturally biocidal as covered previously. Material property challenges with solid desiccants, there's none. The only material handling challenge with liquid desiccants, which we've solved through the closed loop nature of our system, is that liquid desiccants are fundamentally a brine solution, and just like on a coastline, any sort of salty air or salty water, if they touch metal, do degrade it over time. From a dew point depression capability, solid desiccants have exceptional dew point depression capability and can hit negative dew points. Liquid desiccants can't hit quite the dew points that solid desiccants can, but they do have a really strong affinity for water and can still do some significant dehumidification. And then cost point wise, solid desiccants are quite premium. For anyone that's dealt with them, they'd recognize that. It's typically an industrial level price point for solid desiccants. Liquid desiccants are, our innovation surrounds bringing liquid desiccants to an affordable price point, where we're in the realm of hot gas reheat style DOAS price point wise. So how do desiccants save energy, specifically liquid desiccants? To really understand this, to start, let's look at hot gas reheat style systems. So with hot gas reheat style systems, you're going to cool and you start brute force dehumidifying as you hit your saturation curve, targeting a final condition. Once you've reached your final condition and dehumidified as to your target dew point, you leverage waste heat off the compressor, hot gas reheat to bring you back up to neutral temperature. Now, this is fundamentally an inefficient path of operation. When you cross enthalpy lines, you're doing work with a system. And when you're doing work, you use energy. So basically, in this situation here, crossing between this enthalpy line and this enthalpy line, you're doing work that you maybe, or well, I would say you don't want to do because it's overcooling the air just to reheat it back up to temperature. You're wasting energy trying to get the moisture out of the air and using or requiring a bunch of additional capacity to do that. With a liquid desiccant system, and specifically Mojave Arc2Dry, you're still using a DX system to do a portion of the work, cooling, partial dehumidification down, stopping short of your final discharge dew point with that DX system. So only doing the easier portion of the work with the DX system. The reason it's the easier portion of the work is as you get further down and to the left on this saturation curve, those enthalpy lines get tighter and tighter together. You get diminishing returns for the amount of energy input. And what that translates to is bigger coils, more refrigerant, bigger compressors. For each degree colder, you push your subcool on a DX system. So we're eliminating all of that, stopping short of our final target condition with the DX system, and then leveraging liquid desiccant to do the harder effect. I say effect because it's not work, because there's a conservation of energy happening. What this looks like psychrometrically is as the saturated air off that cooling coil passes through the liquid desiccant media, you're converting latent energy to sensible energy in equal parts. So conservation of energy happening. What that looks like is you ride an enthalpy line down to the same target condition without crossing any enthalpy lines, and you save a pretty tangible amount of energy and by eliminating the work involved to get to that same target dew point. And again, you're reheating that air because you're going from a vapor state to a liquid state, and that heat has to go somewhere. So it stays in the air and passively reheats you up to a target condition. Now, going to my comment about reducing refrigerant and being a decarbonization product, we're also shedding this portion of the refrigerant and compressor capacity by leveraging liquid desiccant. So on average, our systems are about 33% smaller on the refrigeration circuit, saving you a significant amount of energy. And that energy saved typically ranges between 40 and 60%. And the reason for that is going back to my example of you work harder for every degree colder you push your subcool on a coil. So your compressor spend is an exponential curve, again, diminishing returns. So by eliminating that portion, we save 40, 50, 60% of the energy spend in dehumidification by leveraging this passive process. And sorry, last thing here, just from an example perspective, in this particular case, with a hot gas reheat style system, it would take about 30 tons of cooling to bring you from 4,500 CFM down to 55 degrees dew point, or dry bulb, wet bulb dew point. With our system, only using about 24 tons of cooling to bring you to that 60 degrees off coil, or pardon me, 61 degrees off coil, and then leveraging liquid desiccant to do the rest of the effect, dehumidifying. And then as a final note, the distance you travel down this enthalpy line is a function of the concentration of liquid desiccant. So if you want to dehumidify further, you reset how much heat you put into that desiccant on the regeneration side. That'll up your concentration and allow you to ride your enthalpy line further. And if you need less dehumidification, say it's a part load day, you back off on concentration, which allows you to travel a shorter distance, not dehumidifying as much. And this is how we're able to actively tune our desiccant system to be, frankly, as efficient as we could possibly be at any given point in time, whether it's a full load day or a part load day. And then a visual here of what's happening as a summary statement within our system. So looking at operation and maintenance, from an operational standpoint, as we unload and do part load operation, we get even more efficient than a traditional refrigeration driven, or like an inverter or variable speed refrigeration driven system. And the reason for that is we're still cutting off that lower corner of the energy that you would need to tackle with a hot gas reheat or vapor compression system in a low ambient day. So letting the liquid desiccant do the bulk of the effect, again, effect because it's not work, to dehumidify in a lower ambient day. Now, a good example of that would be we actually excel in situations where it's part load, and even in situations where traditionally hot gas reheat DOAS struggles. So days where it's, very high humidity content, but not a great or large cooling load. So cool, foggy, rainy day where it's, 65 degrees and a lot of rain outside and a lot of humidity or moisture outside. Traditional hot gas reheat DOAS struggles because it has to overcool the air to dehumidify and then bring that air back up to neutral with hot gas reheat. With our product not requiring overcooling to dehumidify, we're able to really maintain steady dew points where traditional DOAS products cannot. An example of this is we have a unit in Michigan, and this is right out of our cellular telemetry software that we provide to clients. And this is an example of a day where it's cool and rainy, 65 ambient dry bulb, roughly over 12 hours. That's this red line here. We're doing about 2.5 degrees of cooling with a discharge or supply air of about 62 to 63 degrees. And with that ambient dew point of about 57.5 degrees, delivering a stable 45.5 degrees over 12 hours, which is a very challenging condition for traditional hot gas reheat systems to operate in and frankly maintain their dew points as well. So throwing some numbers to this, even at a higher dew point situation, so your conventional 53 to 55 dew point for commercial buildings, you do still see the same level of energy impact. This was an example we looked at in Memphis, where it was for a hospitality application at a 0.4 dehumidification design day, 55 dew point LAT out of this unit. We were about 42% more efficient than the comparable product. And this is over a 15-year useful life, which is our projected lifespan if you service our product properly per recommended schedule or recommended maintenance schedule. And then I would also call out that in this particular case, the client wanted to see a 55-degree off cooling coil. If we had designed around Mojave originally with a 70-degree leaving air temp out of the unit, we would have been able to save an extra roughly $5,500 over the life cycle of the unit by leveraging the liquid desiccant to come off coil at a higher temperature than that 55 and downsizing the refrigeration circuit. Maintenance-wise, all the DX maintenance with our system is the same. Nothing's different on that front. Only maintenance on the desiccant system. There is an additional MERV8 filter protecting the regeneration tunnel. And then those T-strainers, which we've discussed in detail already. And again, from a suggested maintenance perspective, we suggest quarterly filter changes and then inspection of that T-strainer. That T-strainer really only needs to be cleaned when it has debris in it. If you're routinely servicing the unit, it would be rare that you actually need to rinse that T-strainer out unless you're in a very dusty, dirty region. Product warranty, 2-year parts warranty with this product, 5-year compressor warranty with this product standard, which is industry leading for a DOAS. For every other DOAS that I'm aware of, you're paying for that 5-year compressor warranty as an add-on. And then we are providing extended part and labor warranties as well. From a product startup perspective, currently Mojave is starting up all of our products ourselves. We do also start up our products at our factory prior to shipment to ensure no DOAs. And then in parallel to that, we are doing a factory trained technician program, whereas our products are being installed in the market. We are training local technicians to be local experts as well to support our product out in the field. And then eventually we'll move to where factory trained technicians are the first and primary line of people to start up our products out in the field and service them. And we'll move to factory startup or factory technician startup on site being a line item. Application wise, Mojave can really be applied anywhere a DOAS product can go, is the short answer. That said, it's not just a DOAS product, it is a dehumidification product as well. Areas like indoor agriculture, clean rooms, archival storage, and that sort of thing. That's also a great application for leveraging Mojave as not a DOAS product, but a dehumidification product. Additionally, we are seeing this product used as well for pre-treats of solid desiccant systems to downsize that solid desiccant system. So pre-treating that air, bringing that air down to a much drier and cooler condition so that desiccant system, or that solid desiccant system, can be maximized for the cost that a client is going to spend on it. From an application pairing standpoint, Mojave Arc2Dry pairs very well with VRF systems, chilled beam systems, as well as all the traditional hydronic chilled water systems and forced air systems like rooftop units, underfloor air distribution, and VAV. And the way the pairing really is beneficial is by leveraging a lower dew point style design. When you pair a low dew point product with one of these sensible style systems like VRF or chilled beam, you actually are decoupling latent when you leverage low dew point, which is an interesting and newish industry trend where some engineers are looking at pulling latent load off of VRF systems or chill beam systems or rooftop systems. And what that is you're designing around a dry coil and basically condensing no moisture on that sensible system, making it a sensible only system. And what happens as a result of that, you're not wasting energy and capacity trying to dehumidify the air with a system that really wasn't designed for that. And you're moving that latent load over to a product like Mojave that is designed for that. Now, taking it a step further, beyond just shifting load around between one system to another, with Mojave, you're actually taking some or shedding some load. So you're not just moving apples around on a table, taking load from VRF and putting it on DOAS. By leveraging liquid desiccant, you're actually shedding a portion of that load as well. So you're taking an apple off the table and downsizing your net system as a result of that as well. And then taking that a little step further, I do have an example of what a low dew point style building would look like. So let's look now at applying dew point depression for simpler and high performing buildings. To start off, there is a best practice piece that I'd like to touch on. This is right out of an ASHRAE design handbook. It is best practice when you're designing around DOAS systems to push your discharge dew point out of the unit a few degrees lower than your zone condition. And the reason for that is if you're discharging, say you need 55 dew point in zone, if you discharge at 55 dew point right out of your unit, you assume zero infiltration in your space, and that's just simply not going to be the case. And you'll actually wind up, if you're discharging here, you're going to wind up missing your zone condition and float above it and have a space that's out of zone target, really, at the end of the day. So best practice, I would encourage everyone to look at discharging a few degrees under your zone target condition to allow for natural infiltration and frankly, being able to hit your zone condition. So an example of pairing low dew point for a more high-performing design and high-performing building, I would say there's a little bit of a misconception that decoupling latent from a building design is actually more expensive. I would suggest that it is actually not, and we'll kind of run through why. So in an example here where you're pairing the low dew point with a traditional rooftop style system, but I would say this approach is rooftop agnostic. It could be applied to VRF, chilled beam, etc. Rooftop is an easy example. At 95, 80, 67, 5,000 CFM, you could calculate your sensible efficiency at 9.6 EER. If we take that same condition air, 95, 67, but provide a drier version of that air, so at 62 wet bulb instead of 67 wet bulb, you actually get a higher sensible efficiency at 12.3, so that unit's going to run more efficiently because you're not trying to condense moisture on a coil. Additionally, you get a higher effective capacity or sensible capacity out of this unit, and sensible capacity is really the temperature that we could feel in a space. So that's really what we're targeting from a cooling capacity standpoint, ultimately, is the temperature that we could feel and drive a temperature that we could feel. So what does this look like psychrometrically at 80, 67, 5,000 CFM? You're going to do cooling. And once you hit your saturation curve, you start doing dehumidification, which takes work and energy to hit your final target condition of 51 degrees. If you provide drier air, you wind up being in a situation where you don't condense any moisture on a coil. So you're doing primarily, and almost in this case, all sensible cooling. And you just cool and you cool the entire way to your final target condition without condensing any moisture on a coil. And as a net result of that 20 tons to cool and dehumidify drops to about 12.5 tons, 12.8 tons to cool to that same target condition. So saying that as an example perspective, if you have a school, you're providing dry air to all of the rooftop units on every classroom, and traditionally it's been a 5-ton unit on every classroom. At this condition, running 80, 67, when you provide drier air to that rooftop unit, that 5-ton rooftop unit would go from 8067 to 8062, you just went from a 5-ton unit to a 4-ton unit. So from a cost standpoint, you're really shedding costs because you get to downsize all these terminal pieces of equipment as a result of that lower dew point. And again, shifting that load to a DOAS or dehumidification style product like Mojave, you gain the benefit of a higher efficiency on that system as well because it's designed, frankly, for dehumidification. And with our product specifically, you are shedding some load as well by leveraging the desiccant system to do a portion of that work. So you're not paying an energy penalty on the DOAS side, which with hot gas reheat is an energy hog, to do that dehumidification work. And then finally, the EPA does recommend, this was beat to death during COVID, but I think it's actually a very valid message here for decoupled latent designs. The EPA does recommend that indoor relative humidity range, the best range for humans in buildings is between 30 and 50% relative humidity. Designing at 75-50% RH for your turns is fine, but there is the opportunity to decouple your latent, provide a drier space inside, and still be well within and frankly in a more comfortable zone from a IAQ standpoint and a health standpoint within buildings. And then finally, to end things out here, I do have a couple of examples of pairing dehumidification equipment or DOAS equipment with various styles of system. So you have a VRF system here and what that would look like. Similarly, a chilled beam style setup, fan coil style setup, and then a water source heat pump style setup. And then finally, a VAV style setup. Now, a couple other ways this is being applied, specifically Mojave, and with respect to these different systems I've gone through. Mojave units have been used to pre-treat rooftop units in a style like this. Additionally, we have been using our system to dehumidify chilled water systems. And what that means is we're drying out the air being delivered to coils on water source heat pumps or fan coils, drying out that coil to where they're not handling any latent anymore, and doing just pure sensible cooling, similar to what a chilled beam system would do. And as a byproduct of that, you actually get to raise your chilled water temp on your chilled water loop. And when you do that, you see a better kW per ton out of your chiller, as well as a higher effective capacity out of that chiller. So you have the ability to maybe get, rather than 80 tons out of a chiller for original design, you're able to get 90 tons or 95 tons out of that chiller by running a 50-60 delta out of it rather than a 42-52 as an example. A little less front of mind example of how a product like this can pair with a chilled water system to deliver a high performance building. And with that, I do appreciate everyone's time. We do have selection software. I would encourage anyone who would like to sign up and use that. That's available for the public. And then if you want to learn more about Mojave, I would encourage you to check out our website, www.mojavehvac.com. I appreciate everyone's time and hopefully this was valuable.